Have you ever wondered why containers for food, oil, or water look the way they do? From soda cans to milk cartons, companies are constantly manufacturing these containers for countless products. But did you know there's a mathematically perfect way to design them? A way that uses the absolute least amount of material? Today we're going to explore how a cool math concept called optimization can help us find the most economical design for a 4-liter box. Welcome back to David IB course. Today we're diving into optimization, a powerful tool used by engineers, designers, economists, and even in machine learning algorithms. It's all about finding the best possible solution to a problem. Here's our challenge. We need to build a container that holds exactly 4 liters. That's 4,000 cubic centimeters. The container must have a square base, straight vertical sides, and an open top. Our goal is simple but crucial. Use the least amount of material possible. Now, why should we care about this? Well, in the real world of manufacturing, material costs money. Saving even a tiny fraction of metal or plastic on every single container can add up to millions of dollars in savings for a company each year. This is why businesses are obsessed with finding the most efficient design, and optimization is the key that unlocks it. So, let's get started. First, we need to set up our variables. Let us call the side length of the square base x and the height of the container y. The volume of a box is calculated by multiplying the base area by the height. In our case, the base area is x squared. So the volume is x squared times y. We know this must equal our target volume of 4,000 cubic centimeters. This gives us our first equation. X squared times y equals 4,000. This is super useful because it lets us express the height, y, in terms of just x. If we rearrange it, we get y equals 4,000 divided by x squared. Next, let's figure out the total surface area we need to build this container. This represents the total amount of material we'll use. Since the top is open, we have one square base, which has an area of x squared. Then we have 4 rectangular sides, and the area of each side is x times y. So the area of all 4 sides is 4k psi. The total surface area, which we'll call A, is the base plus the sides. A equals x squared plus 4 KIS. Now, here's where the magic happens. We can substitute the expression for h that we found earlier into our surface area equation. This will give us an equation for the surface area that only depends on one variable, x. So, A of x equals x squared plus 4x times the quantity 4,000 divided by x squared. Let's simplify that a bit. The x in the numerator cancels out one of the x's in the denominator, leaving us with A of x equals x squared plus 16,000 divided by x. This is our optimization function. It tells us the total material needed for any given base side length x. To find the minimum possible material, we need to find the lowest point on the graph of this function. And how do we do that in calculus? We find the derivative. And we differentiate the surface area function with respect to x. The derivative of x squared is 2x. The derivative of 16,000 over x is negative 16,000 over x squared. So our derivative s prime of x is 2x minus 16,000 divided by x squared. To locate the minimum point, we set this derivative equal to 0. This gives us the equation to x minus 16,000 over x squared equals 0. Let's solve for x. We can add 16,000 over x squared to both sides, so we get 2x equals 16,000 over x squared. Now let's get rid of that fraction by multiplying both sides by x squared. This gives us 2x cubed equals 16,000. Divide both sides by 2. And we find that x cubed equals 8,000. To find x, we just need to take the cube root of 8,000. And the cube root of 8,000 is 20. So, the optimal side length for our square base is 20 centimeters. We're almost there. Now we just need to find the height. We can use our earlier formula. H equals 4,000 divided by x squared. Plugging in our value for x, we get h equals 4,000 divided by 20 squared. 20 squared is 400. So h equals 4,000 divided by 400, which is 10 centimeters. So there we have it. The most efficient container has a base side length of 20 centimeters and a height of 10 centimeters. What's really interesting here is the final shape. The perfect container isn't tall and skinny, and it's not even a cube. It's actually quite wide and shallow. These are the exact dimensions that give the lowest possible surface area for an open-top box holding 4 liters. As you can see, optimization isn't just abstract math, it's the science behind making smarter, faster, and more efficient decisions in the real world. This is David IB Course, where math meets real life. I hope you enjoyed that. If you liked this video, please hit that like and subscribe button. Don't forget to click the link in the description box below for more interesting videos from David IB Course. Thanks for watching, and I'll see you in the next lesson, presented by David IB Course.